Hello, in this video I'd like to ask the question, what sorts of rectangles are tileable by 1 by n rectangles? And if you think about this for a moment, if one of the side lengths of your larger rectangle is divisible by n, then we can very easily tile it, right? Here I have a 2 by 3n rectangle, and we see that a very simple grid pattern of 1 by n rectangles is able to tile this larger rectangle. But what about other rectangles? Particularly if n is a composite number, it's not immediately obvious that there isn't some sort of configuration of tiles that will allow us to tile a large rectangle where neither of the side lengths is divisible by n. So, well, it turns out that the only rectangles that you can tile in this way are ones where the side lengths, one of the side lengths is divisible by n. And I want to show you a bit of an excessive proof to show you why that is. And it's going to involve introducing a new notion, which I like to call rollability. We say that a region in the plane is rollable if, when you take a sphere and roll it around the boundary of that region, it winds up back in its original orientation. So here we have a region R. I've marked off a specific point where we can start and end our rolling. It doesn't actually matter which point you pick. It turns out that this definition is well defined in the sense that you don't need to worry about what initial point you pick. So let's pick here. And just mark that out so we know that when we've rolled all the way around. And here I have a sphere. It's a very clearly labeled sphere, so we know that it is actually a perfect sphere and not some lumpy juggling ball that I found. So we start our sphere here, and we roll it around. I should also mention that the direction that you roll the sphere around also won't matter. So whatever happens when we roll this way around the region, it's just going to be the opposite of whatever happens when we roll this way. But if rolling this way doesn't do anything, then rolling this way will do the opposite of doing nothing, which is also doing nothing. It will undo doing nothing. As you can see, we didn't quite get back to where we started. So this region here is not rollable, right? So that's what the definition of rollability means. We take a sphere, we plop it down somewhere on the boundary of the region, we roll it around well, I guess you should say we roll it around in a counterclockwise fashion, and that's perfectly fine. It's kind of the traditional direction to go around regions. If we get back to where we started, in the orientation that we started, right? So if the sphere looked like this, when we got back to where we started, then we would have a rollable region, but it didn't. It looked something like this, and so we don't have a rollable region. Okay, so that's the definition of rollability. And this depends a lot on the particular circumference of the sphere that we've picked. And I want to pick a sphere whose circumference is n for a very specific reason. And that is because I want a 1 by n rectangle to be rollable. So let me sketch out one of those for you. Here I have a 1 by n rectangle, and let's try rolling our sphere around the boundary of this rectangle in order to see if it is in fact rollable. So we'll start here on the bottom left corner, and we'll roll the sphere around. And notice that I have very specifically picked the circumference of the sphere to be n so that when we roll along that bottom edge all the way, we wind up back in the original orientation of the sphere. Then we roll upwards 1 unit, and it's going to roll the sphere a little bit. And then we roll back and the sphere here is going to be in the same orientation as it was when it was here, because we've rolled it all the way around, rolling it along this top edge. And then we just roll it down 1 unit. And now it's back in its original orientation. So this particular region here, this 1 by n tile that we're using to tile our larger rectangle, happens to be a rollable region. And now the fun thing about rollability is that here, if we have 2 regions, A and B, and they share a common border, and A is rollable and B is rollable, then the union of the 2 regions is also going to be rollable. Why is that? Well, rolling the sphere along this portion of the boundary will do something to the orientation. We don't expect the sphere to get back to where it started when we roll it from here to here. That's probably not going to happen. It might, and it would be nice if it did, but we're not going to expect that. We're going to say that this does something to the orientation of the sphere. It applies some function to it, and let's call that function f. Now, we also know that taking the sphere from this top point here and rolling it down the common boundary is going to do something else to its orientation. And in particular, we know that it's going to undo doing F, because we know that when we roll around this border here and this common border here, because B is rollable, we need to get back into the orientation that we started in, specifically because B is rollable. So this journey here applies the function F inverse to the orientation of the sphere. On the other hand, let's take a journey around the region A. If we roll upwards around this common boundary, that's actually going to undo rolling downwards around the common boundary. The important fact about rollability. And in particular, if we want to undo undoing F, well, we just need to do F again. So rolling our sphere from here to here along this common boundary is actually going to do the same thing to it as rolling it from here to here. And then finally, rolling our sphere from here to here along this part of the boundary of A is going to undo what happened when we rolled around this part of the boundary of A, because A is rollable. So if we take a journey around the boundary of A and get back to where we started, well, it has to do something and then undo it to get back to where we started. So this journey here does F inverse to the orientation of the sphere. And so taking the entire journey around the combined region, A unioned with B, we'll apply our function f to the orientation of the sphere, and then undo applying the function f to the orientation of the sphere. And so we'll get back to where we started. In other words, the combined area, A unioned with B, is also going to be rollable, again, provided our assumptions that A and B were rollable. So this fact here allows us to say that any region that can be built up out of rollable regions by joining them together along some common boundary is also going to be rollable. And it just so happens that we know that our tiles are rollable. And so if we could take our tiles and tile, it doesn't have to be a rectangle, it could be any shape at all. if we take our tiles and tile it, because the individual tiles are rollable and we're joining them together along their boundaries, the whole region that we've tiled is also going to be rollable. And what this means is that if we can tile a rectangle, let's say that we have some sort of rectangle that's P by Q units large, and suppose that we could tile this by 1 by n rectangles using some sort of technique, then we know that this larger rectangle here also happens to be rollable, just like the tiles that we're using to build it up. And what that means is that we just need to ask, what sorts of rectangles are rollable? Of course, there are plenty of things out there that are rollable, but not tileable, right? There might be a shape like these shapes with rounded borders to them. We could imagine some rollable regions with rounded borders to them. They're not going to be tileable because anything that's tileable by 1 by n rectangles is going to have rectangular borders to it. But nonetheless, it could be rollable. But if it is tileable, then it has to be rollable. And so if we claim that this rectangle, this P by Q rectangle, is going to be tileable, then it has to be rollable. And now comes the gross part. We break out the rotation matrices. We work out the matrix operation of this particular rotation, rotating this sphere horizontally 1 unit. And so we can use that to work out the rotation matrix for rotating this sphere horizontally q units. We can work out the rotation matrix for rotating it up 1 unit, and therefore the rotation matrix for rotating it up p units. And then we can, of course, figure out the rotation matrix for rotating the sphere to the left, q units, and then down p units. And we can multiply these matrices together, and we can see that the product of these is not going to be the identity matrix unless either p or q is divisible by n. And so what that means is that this p by q rectangle is not rollable if P and Q are not divisible by n, and so therefore it's not going to be tileable by our 1 by n rectangles. So I hope you had fun with this video, and I will see you in a future video.